Thread completion. The example above shows how to create a thread. However, what happens if you want to wait for a thread to complete? You need to do something special in order to wait for completion. In particular, you must call the routine pthread join, which is this. This routine takes arguments. The first is of type pthread underscore t and is used to specify which thread to wait for. So it specifies which thread to wait for. This variable is initialized by the thread creation routine. So we have a thread create, which is this. When you pass a pointer to it as an argument to pthread create, which is this my thread. If you keep it around, you can use it to wait for that thread to terminate. So if you keep this, you can use that to wait for a thread to terminate, just like signal and wait, which we will gonna discuss later. The second argument is a pointer to the return value you expect to get. So this is a pointer to the return value that you expect to get. Because the routine can return anything, it is defined to return a pointer to void. So because this routine could return anything, it is using void, just like we discussed in the previous video. Because the pthread join routine changes the value of the passed in argument. So this pthread routine or pthread join actually changed the value of the passed in argument to here, because again it defined the routine can return anything, which use void to return a pointer to void. So because the pthread join routine changes the value of the passed in argument, you need to pass in not just the value itself, but also the pointer to that value. So because this pthread join changes the value of the argument, you need to pass in not just the value here, but also the pointer to that value. So not just the value itself, but also the pointer. As you can see, void asterisk asterisk value underscore ptr. So not just the value, but where that value is located or pointed to. So let's look at an example in figure 27.2 in the code. A single thread is again created and pass a couple of arguments via the myArgT structure. So we create a single thread here and a myArgT structure, which is this myArgT args. So as we created a single thread, which is this pthread, and we impose an argument via myArgT args equals 10, 20. To return the values, the myRetT type is used. So for the actual value, we use this myRetT asterisk rivals, and we have this myRetT asterisk rival equals to malloc size of myRetT. Once the thread is finished, which is this pthread running, the main thread, which has been waiting inside of the pthread, which is this main, then returns, and we can access the values returned from the thread. So after this is finished, we will now be able to access the value returned from this pthread. The value returned by main thread depends on whatever the value of myret t. First, as we can see, so whatever value of this myret t will determine what we return in this main after it returns everything. First, as we can see, oftentimes we don't have to do all of this painful packing and unpacking of arguments. If we just create a thread with no arguments, we can pass null in an argument when the thread is created. So we don't actually need to pack and unpack like this. If we just create a thread, pthread, tp with no arguments, we can pass null in as an argument when the thread is created. Similarly, we can pass null into pthread join, which is here. So here, pthread create, we can see that we don't have to do all the packing and unpacking. As you can see, we pass the null in pthread create. So here, my thread is the input and the arguments of my args in pcreate, pthread create, and pthread join. We just have void and the arvals of the myret t. So similarly, we can pass null into pthread join if we don't care about the return value. So we can also answer. So these arvals are actually return the actual value, and the void returns the pointer p comma void asterisk asterisk. However, similarly, we can pass in null in this if we don't care about the return value, such as in this arvals, because remember, the return of this main will be determined by myret t asterisk rival. Second, if we're just passing in a single value like a long int, we don't have to package it up as an argument. So here we have a long int long int value equals long int arg. So in this case, life is a bit simpler as we don't have to package arguments and return values inside of structures. Here we package and return. In this, as you can see, we don't need myret and myarg. We just we're just passing in a single value like a long int. So we still have null, mythread, args, and pthread join p comma void asterisk asterisk and arvals in join, but sorry, in pthread underscore join, now it's p comma void asterisk asterisk and r value instead of arvals, since we don't have the myret t. So here pthread underscore create p comma null comma mythread, so it's the same with before. Here's the difference: void asterisk 100 instead of and args, since we only have we're only passing a single value. Third, we should note that one has to be extremely careful with how values are returned from a thread. Specifically, never return a pointer which refers to something allocated on threads called stack, like this. myret t oops allocated on stack bud. Because if we return that pointer in this pthread join, what do you think will happen? It will basically in this case the variable oops, which is this, is allocated on the stack of my thread. However, when it returns, the value is automatically deallocated, thus passing back a pointer to a now deallocated variable will lead to all sorts of bad results. So if you return a pointer allocated from a thread stacks, you may end up allocating or returning a pointer that is now deallocated, meaning there's no space available for it, which could lead to all sorts of bugs, because remember, we need to allocate some space for these threads. Certainly, when you print out values you think you returned, you'll probably but not necessarily be surprised, right? Fortunately, the compiler will likely complain when you write code like this, which is yet another reason to pay attention to compiler warnings. Finally, you might notice that the use of pthread create to create a thread, followed by an immediate call to pthread join, is a pretty strange way to create a thread. In fact, there's an easier way to accomplish this exact task. It's called a procedure call. Clearly, we'll usually be creating more than just one thread and waiting for it to complete. Otherwise, there's not much purpose to using threads at all. So usually we create more than one threads and waiting for it to complete first before we execute the other, because remember, the entire purpose of creating this thread is to be able to control how our program runs and to be able to run parallel programs inside one process that share the same data, to be able to avoid the problems that scheduler unpredictable priority does. So we should note that not all code is multi-threaded uses join routine. So not all code use this join routine. For example, a multi-threaded web server might create a number of worker threads and then use the main thread to request and pass them to the workers indefinitely. So sometimes you don't need to join or to end this thread using join. You may need to run them indefinitely inside your main thread. For example, for web server, such long-lived programs does not need to join. However, a parallel program that create threads to execute a particular task in parallel will likely use join to make sure all such work completes before exiting or moving on to the next stage of computation. Again, such long-lived programs thus may not need to join. However, a parallel program that creates threads to execute a particular task in parallel will likely use join to make sure all of such work completes before exiting or moving on to the next stage of computation. So if you're running parallel program, you usually needs some way to synchronize them, so you don't want them interacting with the shared data at the same time. Therefore, you need to use join in that case. So locks, beyond thread creation and join, probably the next most useful set of functions provided by the POSIX threads library are those for providing mutual exclusion to a critical section via locks. The most basic pair of routines are here int pthread underscore mutex underscore lock, argument pthread underscore mutex underscore t asterisk mutex, and then enter line 2 int pthread underscore mutex underscore unlock, argument pthread underscore mutex underscore t asterisk mutex. So this will be the entire section where we lock and unlock uh, our future condition variables and waiter. So that's what we call cond and waiter, which we're gonna discuss later. So these were all this is how we configure these threads in how they sleep or how they wait for other threads to work. These routines should be easy to understand and use. When you have a region of code that is a critical section and thus, so these are the critical section. This is how we lock threads so that they don't interfere with the shared data at the same time. So when you have a region of code that is critical section and thus needs to be protected to ensure correct operation, locks are quite useful. So if we have a critical section or access a region of code that accessing that and needs to be protected to ensure a correct operation and to avoid indeterministic result, these locks are quite useful. So you can probably imagine what the code look like. So like this: pthread mutex underscore tlock, pthread underscore mutex underscore lock, argument end locks, thus x equals to x plus 1 or whatever. So these are the critical, a simple example of a critical region. And then at the end, pthread underscore mutex underscore unlock with the argument end lock again. So here's an example of complete code. So to be able to use this, we need of course to include pthread.h in C, include assert.h, include stdio.h. So we initialize int x equals to 0 and then we semicolon pthread underscore mutex underscore t lock semicolon. So here we keep the code clean, only use if exit okay upon failure. So void pthread underscore mutex underscore lock, argument pthread underscore mutex underscore t asterisk mutex, and then open bracket int rc equal pthread underscore mutex underscore lock argument mutex, then enter assert argument rc equals to 0, then int main. In this int main open bracket int rc equals to pthread. So this is the initialization. Int rc equals to pthread underscore mutex underscore init argument end lock comma null, then enter assert rc equal to 0. Then this is the operation critical section, pthread underscore mutex underscore lock end lock critical section x equals to x plus 1. So these are how we use that in a complete code. So pthread underscore mutex underscore unlock lock, and then it's still in the same main, right? And then the destroy pthread underscore mutex underscore destroy with the argument end lock, then enter print quote x equal percentage d slash n quote comma x, enter return 0 semicolon closing bracket. So this is the example of using that in a full code. If no other thread holds the lock, when we call pthread mutex lock, the thread will get the lock and enter the critical section. So again, if no other thread holds the lock, when we call pthread mutex lock, the thread will get the lock and enter the critical section. So only when others does not hold the lock and this lock is free to use, only we can acquire that and enter that critical section of the variable of the code, because that variable is actually a shared variable inside this whole code. As we can see, that's x equals to x plus 1. So if another thread does indeed hold the lock, the thread trying to grab the lock will not return from the call. until it had as acquired the lock. So if others hold the lock, this thread will just stuck on that because it will not return until it acquire that lock. So until other thread frees it. Though we can actually configure this to wait for a certain time, and then if it still doesn't get the lock from other thread, we can resume it from we can stop it from being stuck in asking for that lock from other threads. Of course, many threads may be stuck waiting inside the lock acquisition function at a given time. Only the thread with the lock acquired, however, should call unlock. So here's an example. Unfortunately, this code is broken in two important ways. So though this is easy to create, this is broken because all locks must be properly initialized first. So later we will see in our full code. In our first lines, we actually needs to initialize these locks, which is our mutex. Thus work as desired when lock and unlock are called. One way to do this is to use pthread underscore mutex underscore initializer as follows. So pthread underscore mutex underscore t lock equals to pthread underscore mutex underscore initializer. So basically equating that lock we initialized earlier to this pthread mutex initializer. Doing so sets the lock to the default values and thus makes the lock usable. So doing actually this makes the lock to its default value, which is free, which make it free to other threads to be used on the code. The dynamic way to do it at runtime is to make a call to pthread underscore mutex underscore init. So that's what we discussed earlier. The int rc equals to pthread underscore mutex underscore init. So we don't necessarily need to initialize this like this if we define that inside the main using pthread underscore mutex underscore init, so that it's dynamic allocation instead of needing to equate that as a variable in the first lines of your code. So the first argument to routine is the address of the lock itself. So the argument for this pthread underscore mutex underscore init initialization is the address of the lock. So where is that? So actually we just put end lock for that because we initialize the lock as mutex already. So that is read by C when we import the pthread.h. So as you can see, also once we have that pthread.h and we int x equals to 0 and then enter pthread underscore mutex underscore t lock, that's where we define the lock. So when we have that argument in this pthread underscore mutex underscore init and lock, it automatically get the lock address, or whereas the second is optional set of attributes. So these are optional, which is the null. So read more about the attributes yourself. Passing null simply uses the defaults. So when we pass null, it only uses the defaults. Either way works, but we usually use the dynamic latter method, which is this. So we usually do the dynamic allocation inside the main instead of using the pthread underscore mutex underscore initializer at the first line of the code. Note that a corresponding call to a pthread mutex destroy should also be made when you are done with the lock. So after you're done with the lock, you need to call the destroy, which is this pthread underscore mutex underscore destroy end lock with an argument end lock as well. After we after we do the operation with the critical section. So the second problem with the code above is that it fails to check error codes when calling lock and unlock. So another problem aside from initialization with that simple code of critical section operation is that it fails to check error code. So again, our strategy is we're gonna relax. We'll start with a simple or assumption, and we're gonna relax this assumption as we get to a more complex and detailed part of the code. Just like virtually any library routine you call in Unix system, these routines can also fail. If your code doesn't properly check error codes, the failure will happen silently. So again, just like any library routine you call in a Unix system, these routines can also fail. If your code doesn't properly check error codes. So just like any routines or any code that we are doing, we need to check or to test it if it's actually work, or we need to provide some error code or some way to test it to be able to make sure that it actually work. So yeah, it's still applicable here, but in this case we're talking more about the error code, like if it's successful it's 0, or if it if it's successful it's 0. If there's an error or it didn't complete, we shall put 2 for us to be able to see if something went wrong. The failure will happen silently, which in this case could allow multiple threads into a critical section. So if you don't have this error code, it will happen silently, so in a background, which is not good because it will access this critical section. Therefore, we will have a race condition, so we will have indeterministic result. Minimally use wrappers which assert that the routine succeed, as shown in figure 27.4. So here we keep code clean, only use if exit or OK upon failure. So void pthread underscore mutex underscore lock with the argument pthread underscore mutex underscore t asterisk mutex open bracket next line int rc equal pthread mutex lock argument mutex semicolon next line assert argument rc equals to 0 closing bracket. So that's an example wrapper. More sophisticated non-toy programs which can simply exit when something goes wrong should check for failure and do something appropriate when a call does not succeed. So here is a wrapper that simply exits if we fail the void pthread underscore mutex underscore lock argument pthread underscore mutex t asterisk mutex open bracket next line int rc equals to pthread mutex lock argument mutex next line assert. So this simply exits, but for a more sophisticated programs, if something goes wrong, you should check for failure and provide the error code, because you can simply just exit or if the call does not succeed. So here's an example of using a wrapper in a complete code. So we still have int x equals to 0, pthread underscore mutex underscore t lock. So wrapper that checks failure without exiting immediately. Sorry, this is an example of um, code that checks for failure without exiting, just like that simple wrapper. So int safe underscore mutex underscore lock. So we're basically defining this function with the argument pthrex underscore mutex underscore t asterisk mutex open bracket int rc equals to pthread underscore mutex underscore lock argument mutex. So if here's what checks or what provides the error checking. If argument rc not equals to 0, open bracket next line f print stderr comma quote error failed to lock mutex argument code percentage d slash n quote comma rc return rc let caller decide what to do closing bracket return 0 closing bracket. So after that that wrapper that checks for failure, that's where the main code, the initialization operation and destroy. So it's still the same with sorry we have a bit different initialization code here if you want to check for error. So int rc equals to pthread underscore mutex underscore init argument end lock comma null semicolon, and if so we still we in next line if argument rc not equals to 0 again open bracket next line f print f argument stder comma quote error. So it's like the error argument we have with the safe underscore mutex underscore lock function or int, and the next line return 1. So instead of return rc we have previously in this initialization we return 1 semicolon which handle gracefully exit or retry then closing bracket. So for operation, which is the critical section, we define rc equals the safe underscore mutex underscore lock argument end lock. If next line if rc equals to 0 open bracket only proceed if lock succeed. Next line x equals to x plus 1, which is the critical section. Next line pthread underscore mutex underscore unlock argument lock semicolon closing bracket else opening bracket the f print with an argument sderr comma quote skipping critical section due to lock failure dot slash end quote, and then closing bracket. Now for destroy we still we initiate we set rc to equal to pthread underscore mutex underscore destroy with an argument lock. If rc not equals to 0 next line f print f argument stderr comma quote warning quote colon failed to destroy mutex code, and then comma rc and then semicolon next line print x, which is the same as the printf in the normal code we discussed earlier. So yeah, that's the example of a more sophisticated program for handling error. The lock and unlock routines are not the only routines within the pthreads library to interact with locks. So the lock and unlock is not the only routines in the pthread library that we use for locks. Two other routines of interest: int pthread underscore mutex underscore try lock with an argument pthread underscore mutex underscore t asterisk mutex. So it's kind of like the argument we have earlier. The pthread underscore mutex underscore t underscore mutex is what we have defined earlier, and then int pthread underscore mutex underscore time d lock. So it's kind of like a function because it's defined as int, right? So the time d lock with the argument pthread underscore mutex underscore t asterisk mutex again, comma, with additional parameters struct time space asterisk abs underscore timeout. So here's the whole code when we want to use this. So int equals to 0 again, we still include the pthread.h and then sddio.h. pthread underscore mutex underscore t lock semicolon, we still have that. So for int main, so instead of having the safe one in a more conservative, sophisticated error code, now instead of that, at the start, here we have the int main as at the start. So we have the initialization, and then we have the operation, so in this operation, this is where it changed, because here we still have defined the rc equals to pthread underscore mutex underscore try lock with an argument lock. However, we have the else now, if else inside it. So if argument rc equals to 0, open bracket, get lock immediately, which is the critical section, x equals to x plus 1. Next line, pthread underscore mutex underscore unlock argument lock else. So here's the difference. So f print with an argument sderr comma code lock bc will wait with timeout. So this is the else, the different. And then the operation again, struct. So these are the time d, another argument, struct time spec timeout. So clock underscore get time, argument clock underscore real time, comma end timeout, semicolon. Next line, timeout.tv underscore sec plus equals 2, wait up to 2 seconds. Next line, rc, we define rc equals to pthread underscore mutex underscore time d lock with an argument end lock, comma end timeout. So this is how we use the time d lock inside, in the else, inside the if operation. And then we define another if for this time d lock. So it is a nested. So next line, if rc equals to 0 with an argument x equals to x plus 1. So these are the critical section. pthread underscore mutex underscore unlock end lock else, we define f print sdderr code time lock failed or timeout, semicolon, closing bracket, and then closing again. Then we close that if else loop. Now we are on the destroy part. So we close that operation. We initialize rc equals to pthread underscore mutex underscore destroy with an argument end lock. If rc not equals to 0, f print, next line, f print sder code warning failed to destroy mutex code, comma rc semicolon. Next line, print code x equal percentage d slash n, comma x. Next line, return 0, closing bracket. So these two calls are used in lock acquisition. The try lock version returns failure if the lock is already held. So this is the first routine, will returns failure if the lock is already held by another thread. The time d-lock version of acquiring a lock returns after a timeout or after acquiring the lock, whichever happens first. So basically, the time d-lock provides us a way. This is what I'm saying when we have a routine or a way to configure the thread to stop waiting at a specified time to request to acquire that lock in case that lock is being used. So for example, if 5 seconds the lock is still not here, we will therefore stop the request. So this is where the time d-lock came from. So as we discover, it's actually came from a routine that's provided by pthread library, which is the time d-lock. So the try lock, on the other hand, returns failure if the lock is already held. So it returns immediately a failure, unlike a time lock which wait for a certain time. So that's the relaxed assumption of how these lock actually wait for other threads to finish using the shared critical section. So here, first, pthread underscore mutex underscore try lock function. Try to lock now. If it's busy, fail immediately. It never waits. It returns 0 if it got the lock. So as you can see in the stderr, or EBC if the lock is already held. So let's go back in the code. Let's see the try lock. So as you can see here, lock BC. So we don't have an error for try lock, because it will if it's busy it will fail immediately. So we don't have a, I mean, in the if else statement we immediately return to the else statement. So instead of getting a standard SDERR, it will return 0 if it got the lock, or EBC if the lock is already held. So if it already held, it will go to its else statement. So for pthread underscore mutex underscore time lock, with the two argument pthread underscore mutex underscore t asterisk mutex comma struct times specs asterisk abs underscore timeout, it will try to lock, but will wait until this absolute time expires. It can wait up to a certain time before giving up requesting for lock. Again, it will return 0 if it succeeds before the timeout, or e timeout if the deadline passes. So if you call pthread underscore mutex underscore time lock function with a timeout equal to the current time, so it's already expired, the function won't wait at all, because you're essentially setting the time to 0, so it won't wait any that thread to free the lock. So it will just check once whether the mutex is available. So the behavior is identical to pthread underscore mutex underscore try lock. So here's a complete example. Initialization, so I believe it's the same. I believe this is the same as the previous course we discussed. Previous code we discussed. There's a slight difference in this code. Let's see. So we still have initialization here. Let's see the previous code. Yeah, so this code is different. Let's discuss this. So we still get the include pthread.h, include sdio.h. Now we include the time.h and include unis std.h. Let me check if we include that in the previous code. Yeah, the time.h was included in the previous code, but we add the unis std.h to include the standard error. So here in the previous code we only have pthread.h included and stdio.h and the assert.h for the introduction of locks. So let's discuss this code. So here, after this, we include this for include pthread.h, include stdio.h, include time.h, include what's this unistd.h. So we initiate the pthread underscore mutex underscore t space lock semicolon, and then next line int x equals to 0. As you can see, we can the order of that does not matter. Earlier we have the int x equals to 0 as the start. So here we start with the int main function, and then we initialize int rc. We equate to p this int rc we equate to pthread underscore mutex underscore init with an argument block comma null. So these are the complete application of the init or everything we discussed earlier. So if rc is not equals to 0, um, open bracket, next line f print sderr comma quote error semicolon failed to init mutex. So quote, so we will provide an error if it's failed to initialize. Next line, return 1 semicolon closing bracket. Now lock mutex once so others can get it immediately. So pthread underscore mutex underscore lock argument lock. So it's kind of like the entire point of locking it, so that other threads or other threads won't be able to access the shared variable once other thread has the lock. So print main thread lock the mutex. So the main thread lock the mutex using that code. Now try lock. First we will try use the try lock with no wait. So we initialize rc equals to pthread underscore mutex underscore try lock with an argument end lock. Next line, if rc equals to 0, open bracket, next line x plus plus semicolon. Next line, pthread underscore mutex underscore unlock with an argument lock. So as you can see, we have that lock and unlock here, and we have the critical section. Closing bracket, else, open bracket, print f, open curly bracket rather, print f pthread code pthread underscore mutex underscore try lock function colon mutex bc no wait, and then semicolon close curly bracket. So these are the code for time d lock. So these are for the operations, okay? So the time lock and time d lock is for the operation. So these are the code for time d lock that waits up to 2 seconds. So struct time spec time out semicolon, next line clock underscore get time argument clock underscore real time comma and timeout. Next time timeout dot tv underscore sec plus equal to, next time rc equal pthread underscore mutex underscore time d lock argument lock comma and timeout. Next line, if rc equals to 0, open curly brackets, next line x plus plus. These are the critical section. X plus plus semicolon, next line pthread underscore mutex underscore unlock with an argument end lock semicolon. Closing curly bracket, else, opening curly bracket, print f code pthread underscore mutex underscore time d lock 2s colon timeout or vc code semicolon and then closing curly bracket. Now these are the code for time d lock with 0 timeout, same as time lock. So it's we start with struct time spec now semicolon, next line clock underscore get time argument clock underscore real time comma end now semicolon slash slash timeout equal so these are the timeout or current time, and the next line rc equals to pthread underscore mutex underscore time d lock with an argument end lock comma end now semicolon. Next line, if rc equals to 0, opening curly bracket, next line x plus plus semicolon, next line pthread underscore mutex underscore unlock with an argument lock, closing semi curly bracket else, opening curly bracket. Next line, printf code pthread underscore mutex underscore time d lock 0 seconds colon behave like try lock semicolon closing curly closing semi-curly brackets, and these are the unlock and destroy. Pthread underscore mutex underscore unlock with an argument lock. Pthread underscore mutex underscore destroy with an argument lock. And the next line, printf again with a code x plus percentage d slash n comma x semicolon. Next line, return 0 semicolon closing curly bracket. So what happens when you run this? So you'll run this using gcc-o mutex underscore demo space mutex underscore demo dot c space dash pthread dot slash mutex underscore demo. So you'll see output similar to main thread lock the mutex pthread next line pthread underscore mutex underscore try lock function colon mutex bc no wait. The next line pthread underscore mutex underscore time d lock 2 seconds colon timeout or bc. Next line pthread underscore mutex underscore time d lock 0 seconds colon behaves like try lock, and the next line x equals to 0. Thus, the time d-lock with a timeout of 0 degenerates to the try-lock case. Both of these versions should generally be avoided. However, there are a few cases where avoiding getting stuck, perhaps indefinitely in a lock acquisition routine, can be useful, as we'll see in the future when we study deadlock. So we should avoid this at all costs, but there's some case where avoiding getting stuck indefinitely in a lock acquisition routine in a deadlock could be useful. So this could be useful. Mimicking the try lock with a time d-lock could be useful in a deadlock. So condition variables. The other major component of any threads library, and certainly the case with POSIX threads, is the presence of condition variable. So aside another routine that is major in threads library, certainly with POSIX threads and any other thread library, is the condition variable. Condition variable are useful when some kind of signaling must take place between threads. If one thread is waiting for another to do something before it continue, so it will signal to the other if thread if it continued, kind of like the signal. We need condition variable because it's one of the most important synchronization tool in the world of threads. So we may think that locks already synchronize that sharing or avoid that sharing of critical section, but this signal actually is more detailed, which we will discuss. That we use or we describe as a concept of condition variables. So it's one of the most important synchronization. This is how you synchronize Google Docs, your notes in your app. So a condition variable con is used with the mutex lock. So it's used with the mutex lock to let threads sleep and wake up in an organized way. So it let the thread sleep and wake up. So again, sleep and wake up, kind of like you sleeping and waking up. So we use like probably an interrupt here or a signal, because we will discuss this in detail further in the next video. So you always hold the lock before waiting or signaling. So you need first to hold the lock before you wait or signal, or before you wake up, or you ask someone to sleep, so that shared data checked by the condition stays consistent. So you hold this before you wait or signal, or before you wake, before you sleep or wake other threads, so that the shared data checked by this condition will stay consistent. So two primary routines are used by program wishing to interact this way. So here we have int space pthread underscore con underscore wait with an argument pthread underscore con underscore t asterisk con comma pthread underscore mutex underscore t asterisk mutex semicolon. Next line, int pthread underscore con underscore signal with an argument pthread underscore con underscore t asterisk con. So it's kind of like the same with the time d, but here the wait has two arguments, or the first routine has two arguments, while the second routine has one argument. Earlier, the time d has two arguments, include the time, the lock, and the time. Here, we have an argument as two for two. We have two arguments at the first routines, which is the pthread underscore con underscore wait, which has an argument of pthread underscore con underscore t asterisk con comma pthread underscore mutex underscore t asterisk mutex. So here, let's discuss it in full code again. So to use a condition variable, one has to, in addition, have a lock that is associated with this condition. So again, to use condition variables, one has to, in addition, have a lock that is associated with this condition. So to be able to use this con wait underscore wait and con underscore signal, there must be lock associated with it, because again, we need to hold lock to be able to wait or signal others to wake up. Or sleep and wake up, so that shared data checked by the condition stays consistent. So again, to use condition variable, one has, in addition, have a lock that is associated with this condition. When calling either of the above routines, the lock should be held. So when calling either of the above routines, which is the con underscore wait and con underscore signal, the lock should be held. So here we only include pthread.h and stdio.h. So we initialize pthread underscore mutex underscore t space lock equal pthread underscore mutex underscore initializer. So we share the lock on that line. Next line, pthread underscore con underscore t space con equals to pthread underscore con underscore initializer shared condition int ready equals to 0 semicolon shared flag. So we have void asterisk waiter with an argument void asterisk arg opening curly bracket. Next line, pthread underscore mutex underscore lock with an argument lock. So lock, it means we will lock it. This line will lock before waiting or before doing the condition or using that cond underscore wait and underscore signal. So while argument ready equals to 0, so it means wait until ready. So next line, pthread underscore con underscore wait with an argument end con comma end lock. So as you can see, these are the argument in application of con underscore wait, the end con and underscore end lock. So it means release lock comma wait So we release the lock and then wait on that line. And the next line, printf code waiter colon receive signal quote semicolon. Next line, pthread underscore mutex underscore unlock with an argument end lock. So unlock after that. As you can see, we still have lock and unlock, but inside it we use the cond. So we use a while, and then after the next line, return null semicolon, and then closing curly bracket. So void signaler. So that is the code for waiter, to create a waiter. These are the code for signaler. Void asterisk signaler, argument void asterisk arg, opening curly bracket, next line, pthread underscore mutex underscore lock with an argument lock. So it means lock before signaling. So we lock first before we signal with cond. Next line, ready equals to 1 semicolon. We change the condition with that line, ready equals to 1. Next line, pthread underscore con underscore signal with an argument con semicolon. So while wake one waiter. So this is this signal is the use to wake. So the wait, the con underscore signal are used to wake up, wake one waiter. The next line, printf quote signaler colon send signal quote semicolon. Next line, pthread underscore mutex underscore unlock with an argument lock semicolon. So unlock after the signal. Next line, return null semicolon, then closing curly semi bracket. So we define that first, the signaler and the waiter. Now after that, we define the main. So int main, open and close parenthesis, open semi curly brackets, and then pthread underscore t. Next line, pthread underscore t, t1 comma t2. So next line, this is we start waiter thread, pthread underscore create with an argument end t1 comma null comma waiter comma null semicolon. Next time, pthread, this is how we start signal thread, pthread underscore create with a quote, with an argument end t2 comma null comma signaler comma null semicolon. Next line, pthread underscore join with an argument t1 comma null semicolon. Next line, pthread underscore join with an argument t2 comma null semicolon. Next line, return 0 semicolon, closing semi bracket. So that's how we use that in full code. As you can see, at the end we have main, and that's how we create and join the waiter and signal. So the first routine, pthread cond underscore wait, puts the calling thread to sleep. So the wait, cond underscore wait, which is the first routine that has two argument, puts the thread to sleep because the cond underscore signal actually wakes up the thread and thus waits for some other thread to signal it. So when you say sleeping, you're waiting for other to signal it, to wake it up. Usually when something in the program has changed that the now sleeping thread might care about. So the thread, other thread might signal that to wake it up if that thread might need or might care about that recently changed data. So here, pthread underscore con underscore wait with the argument end con comma end lock. So that means release lock and wait for relock, right? So yeah, so it's wait for relock, wait comma then relock. So that's what it meant. We release the lock, comma, and then wait for relock. Okay, so that's what the con wait means. It puts to sleep. So this code, pthread underscore con underscore wait, and with an argument end con comma end lock, it means it will release the lock, then it will wait because that's the waiter, right? So it will sleep and then relock. So that's what we have in the waiter code earlier. In after the while argument ready equals to 0, so wait until ready, and then next line pthread underscore con underscore wait with an argument end con comma and lock. So it will release the lock in this line, and then wait, and then relock again, and then printf quote waiter receive signal, and then pthread underscore mutex underscore unlock the lock. So unlock after then return null. So as you can see, we have the argument cond and the lock, because we define the lock as pthread underscore mutex underscore t space lock equals to pthread underscore mutex underscore initializer, which allows us to make that pthread underscore mutex underscore t, right, asterisk mutex, which is the second argument of the routine con underscore wait, to be equals to end lock. So instead of that long, because we defined that early on in our code. So we will continue for a moment. Just take my coffee just a moment, guys. Alright, so a typical usage look like this. We include pthread.h, stdio.h, pthread underscore mutex underscore t space lock. So we initialize is equals to pthread underscore mutex underscore initializer to equate the second argument of the first routine, which is the con underscore wait, to be available. So that's a shared lock. Basically, we're allowing this to have a shared lock. So pthread underscore con underscore t space con equals to pthread underscore con underscore initializer semicolon, which is a shared condition. So this is how we use this signal to be able to know when to wake up and sleep those threads, aside from locking, because again it's the heart of synchronization. So int thread equals to 0 semicolon, which is this line is a shared flag. So we initiate the void waiter. So these are the waiter. So these are the same that code we have earlier. So in this code, after initialization of the relevant lock and condition, a thread checks to see if the variable ready has yet been set to something other than 0. So after we initialize this con underscore t and con and then mutex underscore t, which is the lock, a thread will check if the variable ready has been set to something other than 0, which int ready equals to 0. So that's what void waiter does. Lock before waiting, wait until ready, release lock, wait, relock, and unlock after done. So basically this thread checks to see if the variable has yet been set to something other than 0. If not, the thread simply calls the wait routine, which is the waiter, in order to sleep until, so if it is not set this ready or this critical section set or global shared variable set other than 0, it simply calls the wait routine in order to sleep until some other thread wakes it up. So this will code will sleep the routine until some other code wakes it up. So the code to wake a thread which would run in some other thread looks like this. So the code to wake that, if it changed from 0, is here, void signaler. So we call the waker a signaler. Okay, so enough. Void asterisk signaler with an argument void asterisk arg. Open semi bracket. So again, it's still the same signaler, right? Next line pthread underscore mutex underscore lock argument end lock semicolon, and then next line ready is equals to 1. So we change the condition. So once that change, we will now signal the waiter. So pthread underscore con underscore signal with an argument end con. So wake 1 waiter. So that's what it means, this line. Pthread underscore con underscore signal argument end cond. So as you can see, this end cond was initialized before. By simply writing this code in our signaler, it means it waking the other waiter because we changed the condition to 1. Now, as you can see, like what I've mentioned, the pthread underscore mutex underscore lock with an argument end lock will lock first before signaling, because again, you need to lock first before you signal wake or sleep to other threads. And then after that, next line, after we wake the one waiter with pthread underscore con underscore signal argument end code, next line, printf argument code signaler colon send signal semicolon, next line pthread underscore mutex underscore unlock with an argument end lock, unlock after signal, semicolon, next code return null semicolon, and then closing curly curly bracket. So these are the initialization. Pthread underscore mutex underscore t lock equals to pthread underscore mutex underscore initializer semicolon. So these are the initializers. So basically we're just trying to explain what does part of the code does. Pthread underscore con underscore t space con equals to pthread underscore con underscore initializer semicolon, and next line int thread equals to 0 semicolon are those initialization. Now the thread that checks ready and waits the waiter is here, pthread underscore mutex underscore lock with an argument end lock. So same as after initialization of the lock. So check if ready is not equals to 0. So while ready equals to 0, pthread underscore con underscore wait with an argument end con comma end lock sleep until another thread wakes it up. Then pthread underscore mutex underscore unlock with the argument end lock. So these are the code that checks ready and waits the waiter. So it checks the ready, like while ready equals to 0, it will sleep. But if it change, from 1, as you can see, it's better to understand if uh, the p thread, which is after the while argument ready equals to 0, p thread underscore con underscore wait is indented, because that's actually how the logic works. The sleep under another thread wakes it up, and then p thread underscore mutex underscore unlock with an argument end lock, because those are the you know scoping that critical section. This is actually the exactly the first half of the paragraph, so the waiting behavior. So here the thread that wakes it, the signaler, so p thread underscore mutex underscore lock again, end lock. So ready equals to 1, set ready to non-zero, so semicolon. So we set that to non-zero in signaler. So p thread underscore con underscore signal with and con wake the waiting thread, and then unlock again. So this matches the second half of the paragraph for the word for word. So a few things to note about this code sequence. First, when signaling, as well when modifying the global variable ready, we always make sure to have the lock held, right? So before we signal, we make sure that ptrex underscore mutex underscore lock argument and lock is initiated. So this ensures that we don't accidentally introduce a race condition into our code. Second, you might notice that the wait call takes a lock as its second parameter, whereas the signal only takes a condition, right? We see that. So the wait has the lock as a second condition, or the first routine we introduce in this thread library. The reason for this difference is that wait call, in addition to putting the calling thread to sleep, releases the lock. So in addition, this wait call, in addition to putting that to sleep, so again the wait is sleep, or WS if you want mnemonics for that, it releases the lock when putting the said caller to sleep. So there's two actions here. It releases the lock so again, it's sleeping, it makes the thread sleep. Okay, so this con, or this conditional variables or signal, put this thread to sleep, and releases the lock when the putting that thread to sleep. Imagine if it did not, how could the other thread acquire the lock and signal it to wake up? So how could the signaler acquire the lock and signal that to wake up? So however, before returning, after being woken, the pthread con wait reacquires the lock. So before returning, after being woken up, the pthread con wait reacquires the lock. So after it receives a signal, after it wake up, this thread wake up by the signaler, the p thread con wait, or the waiter, reacquires the lock that it releases to signaler earlier, thus ensuring that anytime waiting thread is running between the lock acquire sorry thus ensuring that anytime the waiting thread is running between the lock acquired at the beginning of the wait sequence, again thus ensuring that anytime the waiting thread is running again thus ensuring that anytime the waiting thread is running between the lock acquire at the beginning of the wait sequence, and the lock release at the end, it holds the lock. So it basically means that it ensures that anytime it runs, it has acquired the lock to be able to uh, initiate its signal or to put that thread to sleep. So that what it meant by at any time the waiting thread is running between the lock acquire at the beginning of the wait sequence and the lock release at the end. So here, it's here inside the waiter function. So here we discussed that again pthread underscore mutex underscore lock, and lock, the waiter starts by acquiring the lock. So this waiter code or function starts by acquiring the lock, thus ensuring that anytime a waiting thread is running between the lock acquired at the beginning of the wait sequence and the lock released at the end, it holds the lock. So next line, while ready equals to 0, next line indented pthread underscore con underscore wait argument and cond comma and lock. So it releases lock. It releases to this line pthread underscore con underscore wait with an argument and con comma and lock. So these are the line that does the two steps. It releases the lock, put the thread into sleep, then reacquire before returning the lock. So again, this one line releases the lock or releases lock. It put the threads to sleep and then reacquires before returning. So it reacquires the lock before returning and then print waiter receive signal. Finally releases the lock afterwards. So this is the step-by-step explanation. At the start, pthread underscore mutex underscore lock with an argument and lock. The waiter locks the mutex to safely check the shared variable ready. So this line, basically this function waiter locks the mutex to safely check the shared variable ready. So it locks first. If it can't lock it, therefore it can't access that critical section. So that what this mean. So second, during wait, pthread underscore con underscore wait with the argument and con comma and lock. Inside this call, two things happen atomically. It releases the lock so other threads like the signaler can change ready. So it can change that ready critical section. It puts this thread to sleep again. Those are the two known action of that line. It releases the lock and puts that thread to sleep. When it signal pthread underscore con underscore signal, it wakes up and automatically reacquires the same lock before returning to your code. So once the signaler return the lock, or since the signaler, like for example the signaler change that ready equals to 1, it will signal this and therefore it wakes up and automatically reacquires the lock. So they are synchronized that way, that if the signaler change that critical section, after that change or unlock or free the lock that it acquired earlier, it will signal this and it will wake it up via this conditional variable or con variable and automatically reacquires the same lock. So after that signal first, after it wake up the threads, it automatically reacquires the same lock it got from the signaler after it unlocks the lock. So after waking, when execution after pthread cond underscore wait, the thread already owns the lock again. So it owns the lock again. That's why you can safely check or use shared data again, like ready, before doing pthread underscore mutex underscore unlock and lock. So if it wakes up after pthread underscore con underscore wait, the thread will wake up and already owns the lock again. Therefore, it can now safely does its code in the waiter, which is this pthread underscore mutex underscore lock and lock. So while ready, pthread, so it can does this like waiter receive signal. So it can now print that after waking. When execution continues after pthread underscore con underscore wait, the thread only owns the lock again because it came from unlock of the signaler. That's why you can safely check or use shared data again, which is the ready equals to 0. Or move that whatever code or logic you want with the waiter, or in that case we print f that waiter receive signal. That's why you can safely check or use shared data again, like ready before doing pthread underscore mutex underscore unlock and lock. So why it matters? So this guarantees that between pthread underscore mutex underscore lock with an argument and lock, and then pthread underscore mutex underscore unlock with an argument and lock, the thread always owns the lock whenever it's running, even across sleep and wake up, exactly as the sentence describes. So one last oddity, the waiting thread rechecks the condition in a while loop instead of a simple if statement. So we use while ready, right? That's while ready equals to 0 line is there so that when the waiter thread wakes up, it rechecks the condition to make sure it's really time to proceed. So once the waiter wakes up, it will check the condition before it can proceed with its own logic. The while equals to 0. We'll discuss this issue in detail when we study conditional variables in future, but in general, using a while loop is the simple and safe thing to do. Although it rechecks the condition, perhaps adding a little overhead. So because it rechecks, it adds a step, or maybe because it's while loop, it adds some time and occupies some more space. There are some pthread implementation that could spuriously wake up a waiting thread. In such a cases, without rechecking, so there's an implementation of pthread library, or there's some routine, or there's some code or function that without rechecking, the waiting thread will continue thinking the condition has changed even though it has not, so it will lead to all sorts of bugs. It is safer thus to view waking up as a hint that something might have changed than an absolute fact. So it is the key is to put this like signal as a signal that something has changed than an absolute fact. So kind of like a way for us to more configure how it works. It's kind of like not an absolute fact, but just signal that something has changed. So in your code, while ready equals to 0, it rechecks the condition repeatedly. So with an indentation. So what it means, the oddity is that you might think this should just be if ready equals to 0. But that would be wrong. So why it must be while, not an if. Spurious wake up. Threads can sometimes wake up from pthread underscore con underscore wait without an actual signal. So sometimes threads are actually waking up without an actual signal from signaler. So after waking, the thread should check again whether the condition read is truly satisfied. Second, multiple waiting threads. If multiple threads are waiting, one signal might wake one thread, but others still need to wait. Again, if multiple threads are waiting, one signal might wake one thread, but others still need to wait. The while loop ensures each thread only continues when ready is not equals to 0. Again, if multiple threads are waiting, one signal might wake one thread, but others still need to wait. So if you have a multiple waiter, one signal may wait one thread, but others still need to wait before it can actually wake up. The while loop ensures each thread only continues when red is not equals to 0. And then third reason, safety rule, the condition variable never stores state. Your program logic must recheck it. So because this cond signal does not check state, the program must recheck it. So in plain English, the while ready equals to 0 line is there to get so that when that waiter thread wakes up, it rechecks the condition to make sure it's really time to proceed. So that's why it calls additive. Looks redundant, but it's actually essential for correctness. So some beginners may think they don't need pthread underscore con underscore wait and pthread underscore con underscore signal at all. They can just use a simple flag variable and a while loop that keep checking until it changes. But so some people might think that we can use a simple flag like here, a shared plug, instead of that con underscore wait and con underscore signal. So let's imagine we don't initialize that lock and cond in our initializer. So here we only have int red equals to 0. We include the same library, stdio.h and then pthread.h. So void asterisk waiter, void and asterisk arg, open curly bracket, printf code waiter colon waiting for signal, semicolon, next line, while ready equals to 0. So here and then semicolon. So spin loop, it wastes CPU cycles, and then printf waiter receive signal, return null, closing curly brackets. And then for void asterisk signaler, we have argument void asterisk arg, opening curly bracket, printf code signaler colon sending signal, semicolon, next line ready equals to 1 semicolon. So that directly changed the flag, and then next line return null semicolon, and then closing curly bracket. And then next is the int main function, pthread open curly bracket, next line pthread underscore t1 comma t2 semicolon, next line pthread underscore create argument and t1 comma null comma waiter comma null, and then pthread create again at nt2 comma null comma signaler comma null. So it's still the same as the previous version, but what happens here is that still the same with the previous version, but we just remove the initializer and we return null at the end of the waiter and the signaler. And yeah, the waiter threads, what happened here is that the waiter thread loops continuously, checking ready equals to 0, and then the signaler thread simply sets ready equal 1. So this works sometimes, but it's a bad design. The problem, CPU waste. The waiter keeps spinning, consuming 100% CPU until ready changes. So the waiter will keep spinning, consuming 100% CPU until the ready or the signaler changes it. Race condition, without a lock or memory barrier, the compiler or CPU may reorder instructions. So may reorder that thread instructions, and the waiter might never see the updated value because the scheduler might do otherwise or might schedule otherwise depending on its timing. So third, no proper synchronization. There's no guarantee of visibility across threads. Even if ready is equals to 1 is set, the other thread's cache might still see it as 0. So these are the correct version, the one we created earlier. We unlock after the print, instead of returning null immediately, we have the pthread underscore mutex underscore unlock with an argument end lock, and we initialize the pthread underscore mutex underscore t space lock and pthread underscore con underscore t space con at the start. So these are the approaches. While ready equals to 0, description BC, waiting spin loop, problem waste CPU, not thread safe. Pthread underscore con underscore wait, proper synchronization, efficient and safe. So this is how we compile it. GCC underscore pthread space con underscore example.c space dash o space con underscore example. If we run it in bash / con underscore example, the expected output, you'll see something like this. Order may vary slightly. So in makefile, signaler colon send signal exclamation, next line waiter colon receive signal exclamation, or sometimes the waiter start makefile waiter colon receive signal exclamation, next line signaler colon send signal exclamation. So sometimes the waiter starts first because the scheduler may switch thread execution order. So don't ever do this because that could cause like unpredictable result like that. Sometimes the waiter, sometimes the signal. Don't ever do this. The following for the following reason. First, if it performs poorly in many cases, spinning for a long time, just waste CPU cycles. Second, it is error prone. As recent research show, it is surprisingly easy to make mistakes when using flags as above to synchronize between threads. In that study, roughly half the uses of this ad hoc synchronization were buggy. Don't be lazy. Use conditional variables even when you think you can get away without doing this. So additional notes. So here where they appear in the code, the pthread underscore con underscore wait in the waiter thread. So this matches int underscore pthread underscore con underscore wait with an argument pthread. So here the con is pointer to the condition variable, because again the con underscore wait argument from pthread underscore con underscore t asterisk con comma pthread underscore mutex underscore t and asterisk mutex, it became end con comma end lock, right? Because the end con is pointer to the condition variable and end lock is pointer to the associated mutex. Must be locked before calling. So that's what we initialize at the first lines of the code. Pthread underscore con underscore signal in the signaler thread. So here, pthread underscore con underscore signal with the argument and con. So this matches int pthread underscore con underscore signal with an argument pthread underscore con underscore t asterisk cond. So here the con pointer to the same conditional variable that the waiter is waiting on, right? Because that library or routine has the same pthread underscore con underscore 3 asterisk cond as their first argument, the weight and con. So why you don't see their definitions? pthread underscore con underscore weight and pthread underscore con underscore signal are part of the POSIX threads pthreads API implemented in your system C library libpthread. So you include them with include pthread.h and link them using -lpthread when compiling. So that's the reason we don't need to explicitly put that. So in bash, gcc con underscore example.c space -o space con underscore example space -lpthread. So the two functions and where they are. In waiter, pthread underscore con underscore wait argument encode comma end lock releases the lock, waits, then reacquire. So this means this line releases the lock. We discussed that this line is called to int pthread underscore con underscore wait in that library or routine. We discuss int space pthread underscore con underscore wait argument pthread underscore con underscore t asterisk con comma pthread underscore mutex underscore t asterisk mutex semicolon. So what it does, the thread must already hold the mutex lock and lock before this call. When it executes, it releases the mutex automatically. That's first. Second, it goes to sleep and waits for another thread to signal cond. Third, when it wakes up after a signal, it reacquires the lock before returning. So when it wakes up after the signal from signaler, it reacquires the lock before returning. So the waiter thread pauses here until another thread signals. So that's what we discussed earlier. We're just repeating it. So in signaler, pthread underscore con underscore signal with an argument and cond wake one waiting thread. So this line is called to int pthread underscore con underscore signal argument pthread underscore con underscore 3 asterisk con. So what it does, the thread must also hold the same mutex lock and lock before signaling. It wakes up one thread that is waiting on the conditional variable cond. So it's wake up the same cond. The waiting thread waiter then reacquires the lock and continues. So compiling and running, all of the code example in this chapter are relatively easy to get up and running, to compile and run. Then you must include the header pthread.h in your code. So the pthread.h, that's how we import that. So for example, to compile or to be able to compile that, we need to import that pthread because we'll be needing that in compiling. So for example, to compile a simple multi-threaded programs, all you have to do is the following: prompt greater than space gcc space -o space main.c space -wall space -pthread. As long as main.c includes the pthread's header, you have now successfully compiled a concurrent program. So again, as long as the main.c includes the pthread's header, this -pthread, you have now successfully compiled a concurrent program. Whether it works or not, as usual, is different matter entirely, because it depends on the threads you create or how you process that con and lock. We have introduced the basics of pthread library, including creation, building mutual exclusion via locks. So this is actually how we implement the mutual exclusion we introduced in the previous video. It was introduced by Dijkstra, and signaling and waiting via condition variables. You don't need much to write robust and efficient multi-threaded code, except patience and a great deal of care. There are other aspects of the API that are interesting. If you want information, type man space -k space p thread on a Linux system to see over 100 APIs that make up the entire interface. However, the basics discussed herein should enable you to build sophisticated and hopefully correct performant multi-threaded programs. The hard part with threads is not the API, but rather the tricky logic of how you build concurrent programs. So it's not the API that's hard, but how you use that API. Aside a trade API guideline, so there are a number of small but important things to remember when you use POSIX threads library or really any thread library to build multi-threaded programs. They are keep it simple. Above all else, any code to lock or signal between threads should be as simple as possible. Tricky thread interaction leads to bugs. So, any code to lock or signal between those threads should be as simple because tricky thread interaction leads to bugs. If you don't understand that, the interaction of that signal and the thread lock, it will lead to bugs. So you must keep it as simple as possible. Minimize thread interactions. Try to keep the number of ways in which thread interacts to a minimum, such as if you don't need to have a unidirectional communication between signals and lock, you don't need to. Try to keep it as minimum as possible. If you just need by the if you just need a unidirectional, then that's good. If bidirectional, then you need to be more careful. So each interaction should be carefully thought out and constructed with tried and true approaches, many of which we will learn about in the coming chapters. Initialize locks and condition variables. Failure to do so will lead to code that sometimes works and sometimes fails in a very strange ways. So you must initialize this lock and con variable because failure to do so will result in indeterministic computer system. So check your return codes. Of course, in any C and Unix programming you should be checking each and every return code, just like the return error we provided in each if else earlier. And it's true here as well. Failure to do so will lead to bizarre and hard to understand behavior, making you likely to scream or pull some of your hair or both. Be careful with how you pass arguments to and return values from threads. In particular, anytime you are passing a reference to a variable allocated on the stock, you're probably doing something wrong. So be careful with the arguments such as the void and the pointer return values we discussed earlier you pass into these threads, because anytime you are passing a reference to a variable allocated on the other stock or on the other thread, you are probably doing something wrong, because that variable is could be allocated and using by other thread. Therefore, you may get these indeterministic results because you need to have a critical section and lock and unlock those part of the code, the stock. So if you're referencing to those, you're likely using the lock and condition. And remember that we need to keep it as simple as possible. Therefore, whenever you're doing this, you're probably need to be more careful. So each thread has its own stock. As related to the point above, please remember that each thread has its own stock. Thus, if you have a locally allocated variable inside of some function, a thread is executing it essentially private to that thread. No other thread can easily access it. To share data between threads, the values must be in the heap or otherwise some locale that is globally accessible. So if you initiate a locally variable in that thread or on that function, therefore you must be careful because that variable is private to that thread. So if you want a shared variable in which you really need that to that program, therefore or process, therefore you put that in the top like we have done with ready, or put that in a heap to be accessible globally, because again every stock has its private variable or every thread. Always use condition variables to signal between threads. While it is often tempting to use simple flag, don't do it. So always use these condition variables to wake up and sleep threads. to be able to put this synchronization to control your app behavior without the scheduler, without being beholden with the scheduler. So always use condition variables to fix the issue with scheduler. Use the manual pages. On Linux in particular, the pthread man pages are highly informative and discuss many of the nuances presented here, often even in more detail. So read them carefully. So here, code recap. We have pthread underscore mutex lock, int thread equals to 0, and two threads create. So that's how we initiate and create. Now, does this code use the heap? No, it doesn't. All your shared variables, lock, con, and ready, are global variables. So these are global variables because we initiate it at the top, which live in the global data segment, not the heap. So it's a global data segment of the code, kind of like in the code section. So it's not in the stock, it's not in the heap, but it's in the code section. It's a global accessible. However, the effect is the same as using the heap because globals are shared between all threads, like heap allocated data. So heap allocated is shared, right? So each thread stock is private to that thread. Explanation: each thread, waiter and signaler, has its own stock. So any local variable inside waiter or signaler is private to that thread. The variable ready, lock, and cond are outside those functions, as we have initialized it at the first line of the code. They live in global memory accessible to both threads. In real applications, shared data is often heap allocated dynamically using malloc. So often, actually, this shared data is in malloc or in heap, especially if you need many locks or variable size structures. Especially if you have many, if you need many locks or if you have many critical section, you often need to put that in a malloc instead of the shared variable. But we just put this for simplicity. Or if you have a variable size shared structure, so if you want to allocate as much memory from that. So summary table stock. No, each thread has its own local variables inside waiter. So that's the stock. Heap, it's a shared across thread, yes. Not used here but could be with malloc. So these are the equivalent if we use malloc. Pthread, so we initialize that at the start again. Pthread underscore mutex underscore t. Asterisk lock equals to malloc size of pthread underscore mutex underscore t. So it's in the first lines again. And then next line, pthread underscore con underscore t. Asterisk con equals to malloc argument size of argument pthread underscore con underscore t. Semicolon. Next line, int asterisk ready equals to malloc argument size of argument int semicolon. Next line, asterisk ready equals to 0. And then next line, pthread underscore mutex underscore init argument lock comma null semicolon. Next line, pthread underscore con underscore init argument con comma null semicolon. Now the shared data lives in the heap but logically behaves the same as our example. So locks, introduction of the locks. From the introduction of the to concurrency, we saw one of the fundamental problems in concurrent programming. We would like to execute a series of instructions, but due to the presence of interrupt of a single processor, so because of that interrupt determine the schedule or priority, or multiple threads executing on multiple processors concurrently, or these multiple threads executing in multiple processors concurrently, because again this has shared memory, but they could run in multiple processors concurrently. We couldn't. So in this chapter, we just attack the problem directly with the introduction of something referred to as lock. Though we discussed that lock already, we will just gonna expand this in more detail. Programmers annotate source code with locks, putting them around critical sections, and thus ensure that any such critical section executes as if it were a single atomic instruction. So locks, the basic idea. An example assumes a critical section looks like this, the canonical update of a shared variable. So balance equals to balance plus 1. Of course, other critical section are possible, such as adding elements to a link or link list, or in the free list or free list to track the free data in our memory, or other more complex updates to shared structures. But we'll just keep up. We'll keep to this simple example for now. To use a lock, we add some code around critical section like this. So here, lock t music semicolon, some globally allocated lock mutex, and then lock argument end mutex. So instead of lock, we have the end mutex semicolon. Next time, balance equals to balance plus 1, and then line 5, unlock argument end mutex. So this is how we unlock it. So a lock is just a variable, and thus to use one, you must declare a lock variable of some kind, such as mutex above. So lock is just a variable, so therefore you need to define or declare a lock variable of some kind, such as the name mutex. This lock variable, or just lock for short, holds the state of the lock at any instant time. It is either available or unlocked or free. So it's either available or unlocked or free, and thus no thread holds the lock, or acquired or locked or held, and thus exactly one thread holds the lock, presumably is in a critical section. We could store other information in the data type as well, such as which thread holds the lock. So we can, for example, if it's the signaler or the waiter, which thread holds the lock, or a queue for ordering lock acquisition. But information like that is hidden from the user of the lock. So we can also, aside from the name, like signaler, we can also put like the queue on how we would provide the lock. For example, if the signal asks first, we can implement an entire priority queue here, kind of like we did with the operating system. Like if the signal and the signaler and then another thread like mousepad thread, for example, if we have a code that puts the mousepad first regardless of the order, regardless if the signaler request first, therefore that mousepad thread will start first. So the semantics of the lock and unlock routines are simple. Calling the routine lock tries to acquire the lock. If no other thread holds the lock, i.e. it's free, that the thread will acquire the lock and enter the critical section. This thread is sometimes said to be the owner of the lock. So if you some thread own the lock and enter that critical section, it means that thread is owner of the lock, even though because that's the thread that's currently accessing the critical section, it means that's the owner of the lock. So whoever is currently accessing the critical section is the owner of the lock. If another thread then calls lock on the same lock variable, mutex in this example, it will not return while the lock is held by another thread. In this way, other threads are prevented from entering the critical section while the first thread that holds the lock is in there. So it's prevented because again, to make it mutually exclusive. So that's what the lock solved, while the condition or cond solved the more synchronization because it used interrupt via signal, so it's fast, but it doesn't provide an absolute fact of how free is the lock is. So once the owner of the lock calls unlock, the lock is now available free again. If no other threads are waiting for the lock, no other thread has called lock and is stuck therein, the state of the lock is simply changed to free. So if there's no other thread asking for that lock or asking to be the owner of that critical section or asking to access the data of that critical section, it is simply changed to free. If there are waiting threads stuck in lock, one of them will eventually notice or be informed of this change of the lock state, acquire the lock, so they will inform probably via condition signal and enter the critical section. So let's say one thread already owns the lock. So here is an example. So p thread underscore mutex underscore lock with an argument lock, and these are the critical section. At this moment, the thread owns the lock. So any other thread trying to do this, p thread underscore mutex underscore lock with an argument end lock will be blocked or paused because someone are holding it, or the owner of that critical section. That means the other thread is waiting or stuck in lock. So that's what it means. But that's what we mean by stuck in lock. So waiting threads are stuck. Stuck in lock doesn't mean the program crash. It means those threads are blocked inside the p thread underscore mutex underscore lock call, waiting for the lock to become free. Don't think of it like they are in line waiting for the door critical section to open. Owner releases the lock. When the first thread calls p thread underscore mutex underscore unlock with an argument end lock, the lock becomes free. So when the first thread called the unlock, it will become free, right? So one waiting thread gets woken up. The OS or pthreads library will then wake up one of the blocked threads which was stuck in lock. So the OS will wake that up using a condition variable which was stuck or requesting for a lock key. That thread noticed the lock is free, successfully acquires it, and enters the critical section and becomes the owner of the critical section. Other threads, if more than one was waiting, remain blocked until it's free again. So other threads waiting, if it's not the first, will remain blocked until it's free again. Lock provides a minimal amount of control over scheduling to programmers. In general, we view threads as entities created by the programmers, but scheduled by the OS in any fashion that the OS chooses. So because the OS could choose to run which in these entities, we need to be able to configure and prepare for that in worst case scenario, even though the OS runs it in this time or in this time, etc. So lock yields some of that control back to the programmer. By putting a lock around a section of code, the programmer can guarantee that no more than a single thread can ever be active within that code. That locks help transform the chaos that is traditional OS scheduling into a more controlled activity.